So hello everyone. So hello everyone. I welcome you all back to our channel. And in today's video, we are going to start with our new series for the preparation of UPSC Engineering Services Examination 2024. So basically, in this through these live sessions, we are going to be completing the syllabus of the engineering services examination, and all these videos will also be useful for those people who are preparing for the gate examination, or they are giving their engineering degree semester examinations, right? So it's going to be a helpful video for all of you. And from today's video, through all the live sessions, we are going to be starting off with digital electronics from today, that is 2nd of September, and we will try to complete the whole digital electronics syllabus specifically till 6th to 7th September, right? We will be that's our target, tentative target, to complete the syllabus till 6th or 7th of September, right? So let's get started now. Very first, we are going to start with our module 1, that is nothing but number systems. And when we talk about number systems, decimal numbers are something that first comes to our mind. Now, what is decimal, right? Basically, decimal means 10. That means it has 10 digits. All the digits from 0 to 9 are considered as decimal digits. Right. So here there's a representation of a digital decimal number. There we have an example of the number 8653. So it is nothing but 8000 plus 600 plus 50 plus 3, right? So if we break this number, we can write it as 8 into 10 raised to 3, because it is on the thousands place, right? Similarly, 6 into 10 raised to 2, because it is in hundreds place. 5 into 10 raised to 1, because it's in tens place. And 3 into 10 raised to 0, because it's in ones place, right? So this is just a simple representation of a decimal number. In case of fractions, we all know before the decimal point, this is how we represent it. But after the decimal point, we represent it in this manner. That is 10 raised to minus 1, 10 raised to minus 2, and so on and so forth. It goes on. These after the decimal points, right? So this is just a simple decimal number representation of a complete number and of a decimal number, right? Okay, now let's move on to the second numbers. That is nothing but binary. Binary means it consists of 2 digits, 2 bits, that are zeros and ones, right? Now how do you represent it? You represent it in this manner. I will tell you a code. 1 second. Yes. So how do you represent it? Whatever number you take, say for example 1011, right? So this number is nothing but our binary number, right? So say for example, I want to convert a decimal number into a binary number. How will I do it? I will use the 8421 code. I will use the 8421 code for a number. So for example, if I take an example of the number 9, right? So what I would do is, this is nothing but 2 raised to 0. This is nothing but 2 raised to 1. This is nothing but 2 raised to 2. And this is nothing but 2 raised to 3. So what would 9 be? 9 will be 2 raised to 3 plus 2 raised to 0. That means 8 plus 1, right? So 8 plus 1 is nothing but 9. So let me just change the color. Yeah, so this is 8 and this is 1. So how will we represent it? We need 2 raised to 3 and 2 raised to 0. So 2 raised to 3 will be represented as 1. 2 raised to 0 will be represented as 1, and all the remaining terms will be represented as 0. So this is how you can see the number 9 in decimal format is 1001 in the binary format, right? So in such a simple way you can easily convert a decimal to binary, right? Yes. Now this is very important to know these two terms, what is a byte and what is a nibble, right? So a group of 8 digits, when we say 8 bits, sorry, a group of 8 bits is called as a byte, and a group of 4 bits is called as a nibble. So these are the two terms that we need to remember, because moving on it is going to help us, especially in microprocessors, right? So let's move on and see. Okay, now what does this talk about, right? So basically why we use a binary system is because it gives us only two conditions. One is 0, the first condition is 0 and second condition is 1. That means there is only two states. One is the on state and the other one is the off state, right? So we have only two conditions, just like a switch, just like a simple switch, right? Now if we compare the logic 0 and logic 1 in terms of signal, then we can say that if a signal has voltage between 0 volts to 1 volts, then the range is called as logic 0, right? And when it is from 3 volts to 4 volts, then it is called as range logic 1. Range logic 1, right? So this is a simple representation which you can understand of logic 0, what logic 0 is and what logic 1 is, right? Now let's look at this. Yes, I have already shown you an example of how to convert decimal to binary. This is just a simple graph that is telling us how the base would change, right? So decimal number systems has the base 10. One second. Yes, decimal number systems has the base 10. Binary number system has the base 2. Octal number system will have base 8, and hexadecimal will have base 16, right? So we will learn all these number systems in detail, but it's important to understand the different base of different number systems, right? I will show you the conversion as well, right? Okay, so this is a simple a conversion of an integer from decimal to another base, right? So say for example, oh yes, they have given an example. See, this is base 10, that means this is a decimal number system, and we are going to convert it into base 2, that means a binary number system, right? How did they do that? Okay, this is a different method of using the integer quotient and remainder, but the easy method that I've told you is the 8421 technique that you can use, right? So you have to find the digits which sum up to the given number. In our case, it is 13. So 8 plus 4 plus 1 is 13, right? So what we do is, all those digits which sum up to the number 13, we represent it as 1, and the number which doesn't, we represent it as 0. So in this manner, using the 8421 technique, you can easily within few seconds convert a decimal number to a binary number. So especially while we are giving our exams, especially ESE and Gate, we need to solve all the questions in short given period of time, right? So this is very important. It's a small simple technique, right? Now this is nothing but conversion of a decimal point, right? In case of decimal point, what we do is, one second, I will show you a table first which would help you. Yeah, you can see this, right? So basically how does it go? This is not this table nothing but shows you the growth of binary numbers, right? So basically what we do is 2 raised to 1 sorry, 2 raised to n is our formula, and as we go on changing the value of n from 0 to infinity, we get the different values of 2 raised to n, right? And when we need to convert a decimal number into binary number, what we do is we just find the elements that sum up to the given decimal number, right? So this is a simple technique that we can do. Next is binary addition. Now it's very simple here. What we have taken two binary numbers. Okay, yes. Before that, let me just draw a table over here. Let's see. So 0 plus 0 is equals to 0. This is binary addition I'm showing. 1 plus 0 is 1. 0 plus 1 is 1. And in case of 1 plus 1 binary addition, our answer, the sum is 0 and carry is 1, right? So you can just remember this short table. Okay, once again I'll just redraw it. One second, I'll draw it here. Let me just change the ink color. Yeah, okay, so say this is our first binary digit A, second binary digit B, the sum value and the carry value, right? Okay, so this is our table. Right, this is our table. Now let's put in our digits. Yes, the first one is A is 0, B is 0, then the sum will be 0 and the carry will also be 0. Say A is 0, B is 1, then the sum will be 1 and the carry will be 0. Similarly, A is 1, B is 0, sum is 1 and carry is 0. And the last condition, when both the digits are binary 1, then the sum will be 0 and the carry will be 1. Right? So remember this table, and this is a simple example that we've taken. We've added these two digits. So the first digit is nothing but 11101. So this is A, this is B, right? So you can see over here, we would always start from the least significant bit. Yes, so 1 plus 1, the sum is 0, so we've written it over here, and the carry goes 1, right? So again you added 1 0 1. So 1 plus 0 is 1, right? 1 plus 0 is 1, and 1 plus 1 is sum 0 carry 1. Similarly, when you keep on adding this using this table, this is the answer that you get, right? Now I have an example for you. I'll give you an example over here. Pause the video, try solving it and give me the answer in the comment box. Try adding 0 1 1 0 1 plus 1 1 0 0 1. Try adding these two binary digits, pause the video and give me the answer in the comment box, right? Yes. Now next is, okay, yes. Now the next thing is converting. Okay, before the conversion, let's first understand what octa numbers are. So octal numbers or octa number systems is nothing but, the name says it, octa means 8. So it would have 8 digits starting from 0 to 8. Right? Now how would be the octa representation would be? So whenever we have to convert any number, any say octa, any octa number, any number with octal base to its decimal equivalent, what we do is we multiply it with 8 raised to n. That means the least significant bit of the given number would be multiplied by 8 raised to 0, and the most significant bit of the given number will be multiplied by 8 raised to n. Right? So this is how we do it, and after the decimal point you multiply the given number, just invert the sign, you change the sign, 8 raised to 1, 8 raised to 2, 8 raised to 3 and so on, right? Now you can see over here, let's look at an example. Okay. Okay, there's no example given. Okay. You can pause the video and try solving. I'll give you an example. You can take the number 6, 3, 4, 5. Right? Now this is a octal number and you need to convert this into the decimal equivalent. What would be the decimal equivalent? Pause the video, try solving it and give me the answer in the comment box. Right? Yes. Now next is hexadecimal. Right? Now hexadecimal means, what does hexa mean? Hexa is 6. And what is decimal? Decimal is 10. So when you combine hexa and decimal, it becomes hexadecimal. That means it is going to have 16 digits. Right? Now, what are these 16 digits? I'll tell you. First is our decimal, right? So these decimals, we will have digits starting from 0 to 9. And we will have 6 digits starting from the alphabet A till alphabet F. Right? So the value of alphabet A will be 11, B will be 12, so on and so forth. The value of F will be 16. Right? So this is the representation of hexadecimal number system you can see over here. Right? Now, how do you convert it then? Same. It is hexadecimal, right? So the base will be 16. That's why while converting a hexadecimal into a decimal number system or any other number system, what you do is you just multiply it with the base 16, right? So you multiply the least significant bit with 16 raised to 0 and you multiply the most significant bit of the given number with 16 raised to n, right? So on and so forth, right? So this is a simple representation of hexadecimal and I've told you how you convert a hexadecimal number into a normal decimal number system. Right, now let's just put everything together. Now this is a table which can be very useful for you. You can take a screenshot of this video. In this they have given the decimal number starting from 0 to 15 and they have given the equivalent in binary number system, in octa number system and hexadecimal number system. Right, so you can pause the video and you can see this generally, okay, because it would help you, in the conversions and everything. Right, so do pause the video and watch. Yes, now moving on. Okay, converting a base 16 to base 2, we have already seen this. This is just a detailed explanation. Right, now how does the base change? Let's see. Okay, so first of all what we do is we are going to determine a 4-bit value for each hexa digit. Now over here there are 4 hexa digits, 3, A, 9, F. Right, so I'll write it over here. One second, let me just change the ink color. Yeah, so the first one is 3, the second one is A, then we have 9 and then we have F. Now what we have to do is we have to write the hex digit of each. The hex digit of 3 will be 3 itself. The hex digit of A will be 10. The hex digit of 9 will be 9 itself. And the hex digit of F will be 16. Simple. Now what we do is we will convert these hexadecimal digits into binary. Right? Now what is the binary of 3? Binary of 3 is 0, 0, 1, 1. Binary of 10 is 1, 0, 1, 0. Then we have 9. 9 is represented as 1, 0, 0, 1. And then we have 16. So 16 is 1, 1, 1, 1. So in this simple manner, first we had base 16. We converted the base 16 to base 10. And then we converted it to our binary base 2. Right? So in this simple method also you can convert it. Right? to base 16 to 10 and 10 to 2. Right? Done? Okay. Now this is in case of base 2, right? So we had to convert base 16 to base 2. That's why we considered 4 digits, 4-bit value of each, right? Now let's see what happens in case of converting base 16 to base 8. Okay, so it's the same thing. First we convert the base 16 to base 2, right? After converting the base 16 to base 2, what we're going to do is we're going to regroup the bits into groups of 3 starting from the right hand side. Right hand side means the least significant bit, right? And then we ignore the leading zeros, and each group of 3 bits will become the octal digital bit, right? The same thing that we have done over here. One second, let me just erase the extra ink. See, this is the previous example. In this case, what we had done is we had taken 4 bits over here. Now instead we will consider 3 bits. I will just change the ink color. Yeah, I'll consider 3 bits. 1, 2, 3, 2, 3, 2, 3 and 2, 3. Right? So over here, this is a clearer picture of it. This is the same thing, but they have just considered 3 bits over here, right? And then they have written the decimal equivalent that gives us the octal digit, right? So this is a simple conversion of base 16 to base 8, right? Now let's see how to represent signed numbers, right? Now yes, decimal numbers, plus sign and minus sign is used in decimal numbers. We are aware of this. So if this is our binary number system, this is our 0. This side we would have all the negatives, and this side we would have all the positives, like positives as in positive sign numbers, right? Now in case of computers, we all know that we require we use the binary decimal number system, right? And in binary decimal system we have 2 bits, zeros and ones, right? Now there are 3 types of signed binary representations that you need to know, right? First one is the signed magnitude, second one is 1's complement, and the third one is 2's complement, right? Okay. Now in each case, as I've already told you, the leftmost bit, that means our least significant, most significant bit, right? The most significant bit, left, they have mentioned left, would indicate the sign. Now this sign would now how would we determine if it is positive or negative? Yes, on basis of 0 or 1. So if it is 0, then we say that it is positive, okay? And if it is 1, we say it is negative. This is something you need to remember, because generally we associate 0 to minus and 1 to plus, right? But here it is the other way around. When it's 0, it indicates positive, and when it's 1, it indicates negative, right? So now you can see over here, this is binary number 10, and over here they have written the this is decimal number 12, and over here they have given the binary equivalent, right? Now as they have said, the most significant bit, that means the bit on the left side, would represent the sign bit, and all the remaining bits would be the magnitude, right? So over here it is 0. Over here, see, the left bit is 0. So the decimal value of this binary number is plus 12. Okay. Now in this case over here, look at the second example. Over here it is 1. So 1 means negative sign bit. So the decimal value will be minus 12. Right? So this is the first type of our binary number representation. This is called sign magnitude, that you need to remember, right? Okay. Now next is 1's complement. Now 1's complement is very easy. Now it is just that you have to invert. Okay. When I say complement, you invert. Invert as in 1 becomes 0 and 0 will become 1. right? So now it says ones complement, right? So you will invert the given number only once, right? So you can see over here, look at this. This is an example that they have given. What will be the ones complement of this number? So you can just invert all the given digits. 1 becomes 0 and 0 will become 1, right? Yes, now this is an important point that you need to remember. If there is an n bit number, what will be the ones complement? Remember this formula. The ones complement will be 2 raised to n minus 1 minus n. Right? Remember this formula because there was one of the previous year questions where we had to know this formula in order to solve the question. Right? Okay. Now, how do you find negative of ones complement? Just take the ones complement. Right? Very easy. Now see, what would happen when you convert it? Because when you take the inversion of the positive, it becomes the negative. Because see, over here there is 0. When we invert 0, it becomes 1. And when the sign bits change, what happens? Positive becomes negative or negative will become positive. Right? Yes. Now let's move on to 2's complement. 2's complement is even more easy. So how do you do it? When there is a number given n, any number given n, first you take out the ones complement. What would be the ones complement? Just invert the given numbers. 0 becomes 1, 1 becomes 0. And then whatever number or whatever value has been obtained after ones complement, you add the digit 1 to it. Right? I will show you an example so that you would understand it better. Yeah. So over here you can see. Okay. What would we do first? Just consider this example. This is our given number n. Okay, so the first step is to find out the ones complement. This is the ones complement that we have found out. See, 1 becomes 0, 0 becomes 1, and just find the ones complement and then add binary number 1 to it. Right, so when you add binary number 1 to it, this is the answer you get. Over here it's 0, the least significant bit is 0 in this case. So 0 plus 1, 0 plus 1 is nothing but 1. So this is our answer and this is our 2's complement. Right? Okay, let me just go to the previous slide. Yes, this is the formula you need to remember to find out n bits to complement. Right? This is 2 raised to n minus 1 minus n plus 1. Right? And for one's complement it was 2 raised to n minus 1 minus n. Right? You just add plus to it. These are the two formulas you need to remember. Right? Okay. Now this is 2's complement. Yes. Now this is 1's complement. Okay. This is just an example. So what would be what did this example says is they have given us two binary numbers. Yes, and they have asked us to add them. Right. So first, what did they do is okay. So this is binary number 12. This is binary number 1. Okay. And what they did is they first converted or just found out the ones complement and then added it, right? So what did they do? Add the step 1 is to add the binary numbers. Okay, now what happened is okay, in this case there was a carry that was generated, right? There was a carry that was generated, and whenever there is any kind of carry that is generated, what we have to do is we just have to add this carry to the result. In this case, the carry is 0, so they have just added the result with 0. But if in some cases, if the carry is 1, then you add the result with 1. Right? So in this case, we can find out the addition of two binary numbers. Right? Now, when they say ones complement addition, just find out the ones complement and then add the numbers. Right? Similarly, ones complement subtraction. What would be the subtraction? Same. Find out the ones complement and then subtract. Yes, very simple. Okay. Now next. Yes, now this is 2's complement addition. Similar, very similar. Whatever numbers or whatever binary numbers have been given, just find out the 2's complement for that number. How do you find the 2's complement? Once again, revision. First step is to find the 1's complement and then add plus 1 to the result. Right? Yes, very simple. Okay. Now, in case of 2's complement addition, we ignore the carry bit. But in case of 1's complement addition, we add the carry bit. Right? This is something you have to remember. The examiner can trick you in such questions. Remember, 1's complement may you will add the carry. You will add the carry bit. Very important. And in case of 2's complement, you will ignore the carry bit. Okay, very important. Especially while solving such questions, because already when you give the exams, you're already under such pressure. You might make such silly mistake by ignoring this step. Right, now this is the 2's complement addition. This is also very similar. What we do is, we will first find out the 2's complement and then you will add or subtract. In this case it's subtract, so you will subtract. And same thing, step to remember, this third step is very important. You will ignore the carry bit because it is 2's complement addition or subtraction. Subtraction. Right? Okay. Now this is an example over here given. Pause the video. This is the homework sum that I want to give you. You need to find out, subtract 13, decimal number 13 minus decimal number 5 using the 2's complement subtraction method. Right? This is a simple example that I want all of you all to do. Right? Okay. Now let's move on to our second module. The first module was number systems. Let's just summarize what we have done till now. We have seen the different decimal number systems. We have seen different number systems. First one was decimal number system. Then we studied the binary number system, which is base 2, octa number system, which is base 8, and then we saw the hexadecimal number system, which is 16, right? Then we saw the types of binary number system. First one was a significant bit. So the most significant bit of a given number will be called as the sign bit, right? And in case of the sign bit, when it is 0, it is a positive number, and when it is 1, it is a negative number. Right? This is what we saw. Then we saw the 1's complement. 1's complement is very simple. Just invert the digits. 1 becomes 0 and 0 becomes 1. Then we saw the 2's complement. 2's complement is nothing but, once again, 2's complement is nothing but 1's complement plus 1, which will give you the final result. Right, so this is a simple quick revise of whatever we have studied till now. Now let's study the Boolean algebra and concepts of Boolean algebra. Right? Yes. So this is just a slide which is just giving you an overview. Right? So first of all, we are going to be seeing the different logic functions with zeros and ones. We will study the different truth tables of the gates. Gates are basically the digital circuitry, basics of logic circuits and everything we are going to study. We will see the logic symbols, waveforms. We will study the properties of Boolean algebra. Right? Okay. So let's start with it. Now, very simple, digital system. Now, what is a digital system? A digital system is nothing but a simple circuit which consists of a simple circuit which has inputs and which has outputs. Right? So, basically, we determine binary outputs for each input. Right? So, Boolean algebra helps us in this. Right? It will help us determine the output. Right? Now, let's start with the first circuit. Okay, one second. Yeah, let's just start with our first circuit, or this circuit is also called as a inverter. Yes, it is the basic logic function, right? The very first logic function that you need to remember, and this logic function is also called as NOT function, right? So it's also called as an inverter, or it's also called as a NOT function. This is a simple, this is the symbol of this circuit. It is nothing but what happens, it inverts. So whenever the input given is 0, the corresponding output will be 1, and whenever the input given is 1, the corresponding output will be 0, right? It's a very simple circuit. It's called as an inverter, and this function is called as the NOT function, right? Okay, this is the truth table that you need to remember, and this is the symbol that you need to remember, right? Now let's move on to our next function. I'm sure you have already done this in your graduation. We are just going to have a quick revise of this. Right now, next is our AND gate. This is the symbol of AND gate. And AND gate, we can say that it is very similar to, okay, I'll draw a simple circuit. Say for example, we have two switches connected in series, right? Okay, this is our input battery, and say as an output we have a bulb. Okay, so this is our switch A and this is our switch B, right? So what would happen, unless and until, okay, sorry, yeah, one second. Okay, yeah. So we have our two switches. This is switch A and this is switch B. So unless and until both the switches are in the on condition, both the switches, listen to me carefully, I'm saying when both the switches are in on condition, only then the bulb will glow, right? So this is the circuit, and this is how our AND works. It has two inputs A and B, and it has a single output Y. So you can see in the truth table. So if A is 0, B is 0, that means switch A and switch B are in the off condition, the output will be 0. Similarly, if any of the one switch is on and the other is off, so if A is 0, B is 1, A is 1, B is 0, in both these conditions the switch will be off or the output will be 0, right? So what is AND? We would require both the inputs to be positive. So if A is 1 and B is 1, only then our output Y will be high, right? So yeah, instead of on and off, we would say if it is 0, we consider it as low state, right? And when it is 1, we consider it as the high state, right? Okay. So this is the simple AND gate, this is the truth table, and this is the symbol. Now let's moving on to the OR. What would be the simple circuit or the equivalent circuit of an OR? Two switches, but two switches connected in parallel condition. Two switches connected in parallel condition. Right? So how will it work? This is our switch A, this is our switch D. So how will it work? If any of the switches on, or both the switches are on, our bulb will glow, right? So you can see if A is 0, B is 0, the output will be 0, right? That means low state. But if any of the output is high state or both the outputs are high state, then we would have the output to be 1 or the high state, right? Yes, so this is the function of OR gate and this is the symbol of OR gate. Now let's move on to the different waveforms. Okay, now this is the waveform representation of the gates that we have studied till now. So you can see this is the input X that we have considered, right? This is the second input that we have considered Y, and over here this is the waveform of our first function and second function and third function, right? So let's just consider the first bit. I'm just considering the first bit. So the first bit is 0, the second input bit is 0, then what will be the AND function? AND function will also be 0, right? In case of OR, it will be 0 because both the inputs are 0, then in OR the output is 0. And for NOT, NOT is nothing but our inverter. Yes, so our input is 0, then what will be the NOT output? Yes, it will be 1, right? Similarly, I'll take one more bit. I'll consider the second bit. In the second bit, X is 1, Y is 0. And what will be AND output? AND output will also be 0, because in case of AND, we require both the inputs to be in the high state. In case of OR, any one of the input is high, then the output will also be high, right? Similarly, in case of NOT, we invert it. So our input is X. X is 1. So X naught will be 0. Right? Yes. Now what I want you all to do is create a simple truth table of these waveforms and put it in the comment box. Right? I will erase the ink on the slide. 1 second. Yes. Now you can take a screenshot of this or just pause the video and try creating a truth table of this given waveforms. Right? Pause the video and do it. Right? Okay. Now let's move on to the next. Yes. Now what is the next thing? Next in here, we have considered 3 inputs. Right? Just now we saw 2 inputs. Now we will consider 3 inputs. Now what would happen if we consider a 3 input OR gate? Right? 1 second. Let me just draw the truth table of the OR gate over here. You might be familiar. These are our 4 conditions. Okay. Now in case of in case of 2 inputs, this will be the truth table that I'm just drawing on the left hand side. In case of 3 inputs, the truth table will change, but the logic will be same, right? So say these are our 2 inputs. So 4 combinations: 0 0 0 1 1 0 and 1 1. So what will be the output for OR? Any one is high state, the output will also be the high state, right? So now look at this table. Look at this table. There are 3 inputs, so there will be 8 combinations, right? You might be knowing this formula, 2 raised to n, right? So in this there are 3 inputs, so our combinations will be 8. That is nothing but 2 raised to 3, right? Okay. So you can see over here, if any one of the input is high, or if all the inputs are high, the output will be high, because this is a OR gate, right? So if we give a algebraic representation, if we give an algebraic representation to a 3 input OR gate, then what will it be? It will nothing but be the sum of all the inputs, that is A plus B plus C, right? Very simple. Okay. Now let's move on to this. Okay. Now how do you interpret this? Okay. In case of Boolean functions, dot is nothing but considered as AND function, and plus is considered as OR function. Okay. Just now we saw when it's an input OR gate, then the output will be addition of all the digits. Okay. But if it's an AND gate, say if I consider an AND gate, say 2 input AND gate, I'll consider this is my A and this is my B. So in case of a 2 input AND gate, the output will be the multiplication, we can say, of the digits. So dot represents multiplication, right? So if A is 0, B is 1, output will be 0. But if both are 1 only, then the output will be high, right? So that's why in case of Boolean functions, dot is represented as and plus is represented as OR. right? Very simple. You need to know this. Okay. Okay. So, I'll just read this out. It's just telling us what Boolean algebra is. So, it is nothing but defined as a closed algebraic system containing of a set K or two or more elements with only two operators, that is dot and plus. And I've already told you what they mean. Dot is nothing but, and I know I'm repeating this, but you need to put this in your mind because it is very important. Because sometimes we make, not sometimes, but we do commit such silly mistakes in our exams. Missing the dot, missing the plus sign, right? Yes. This is very important, you need to understand, right? So it contains two operators, plus and dot, right? Okay. Now they have just identified the elements over here. Now 0, I've already told you, it is the identity of plus operation, and 1 is the identity of dot operation in case of Boolean algebra, right? Now let's look at the different operators and the different properties, right? The first one is nothing but the commutative property. Yes, so if our two conditions, you all know this, we've already studied this in algebra, but it's very same for Boolean as well. So a plus b is equal to b plus a, and a into b equals to b plus a. This is the commutative property that we already know. Then what is the associative property? This is also we have studied in algebra. Let's revise it. A plus b bracket b plus c is nothing but bracket a plus b plus c. Similarly for dot operation, a dot bracket b plus c equals a bracket a dot b into c. Yes, so these are two basic properties, commutative and associative. Now next is distributive property. Yes, now this is, you have to remember, a plus b into c equals a plus b dot a plus c. Yes, now next thing is the complement of a. Okay, now basically complement means we've already seen this is nothing but one's complement. So when we say complement, you just invert it. So say if the value of a is 0, then a's complement will be 1. Similarly, if a is equal to 1, then a's complement equals to 0. Right? This is very simple that we have to understand. Okay. Now next is nothing but the principle of duality. Now what this says is, one second, yes. If an expression is valid in Boolean algebra, the dual of that expression is also valid. Right? Now let's see what this dual of expression means. To form the dual of an expression, replace all plus operators with all dot operators. Right? So operators with plus operators, all ones with zeros, and all zeros with ones. Right? Okay, now this might be a little confusing, but I'll take an example. The formula over here. Okay, I mean the example time over here. So see, it is a plus b into c, right? So what they have done is it's equivalent to now a plus b dot a plus c, right? So this is nothing but the principle of duality, right? Now let's move on to the involution theorem, right? Now we can say this is nothing but, okay, wait. Let's first understand what a 2's complement. Okay, this is the representation of A's 2's complement. So obviously A's 2's complement. Okay, now this is not 2's complement. It's actually inverting the number twice. In case of 2's complement, you will add 1, right? But in this case, what they are doing is they are taking 1's complement twice. 1's complement, they are taking 1's complement twice, right? So first, if A is equals to 0, what will be the 1's complement? It will be 1. Then the new value of A will be 1. Then take the 1's complement once again. That means A will again be equal to 0. That's why this is nothing but A double dash is equals to A. Okay, now Remember that a into a dash equals to 0 and a plus a dash is equal to 1. Yeah, this is something you also need to remember. This will also help you when solving the Boolean algebra sums. Right? Okay. Now, taking the double inverse of a value will give you the initial value. This is what we have said. This is nothing but the theorem of involution. Right. Now, next is absorption. Okay. Now this theorem states that a plus ab equals to a and a into a plus b equals to a. Okay, now this is the proof of the theorem, but you can directly remember this theorem. Oh, 1 second, I'm sorry. Okay, yeah. Just remember this theorem, make a table or just make a sheet wherein you will just write down all the statements of all the different theorems because you would have all the theorems on a single page that will help you in solving the sums. So this is the theorem of observation that says a plus ab equals to a and a into a plus b is also equal to a. Right? Now next is the De Morgan's theorem. It is one of the most important theorems in De Morgan's that says a plus b bar or a plus b dash equals to a dash into b dash and a e whole dash equals to a dash plus b dash. Okay, directly remember this theorem. It's very important. Directly remember this theorem. Over here they have just given an description of the theorem, but just remember the statement of the theorems. Right? Now, this is how this is the simple summary of we have what we have studied till now in the module 2. First of all, we saw the basic functions and, or, and not. Then what we saw is the Boolean algebra, what it means, and we saw the different rules of algebra, associative, commutative, and distributive properties. Then we saw the insolution and the De Morgan's theorem as well. Right? Now let's move on to the more logic functions. Now we already saw and, or, and not. These functions are called as universal logic functions because all the remaining functions can be derived from these basic functions. Right? So these are called as the basic functions or universal functions and, or, and not. Right? Now let's move on to the derived functions which are NAND, NOR, and XOR. Right? Okay. So all these three functions are again 2 input and we can also add a 3 input gates to it. Okay. Now converting between sum of products and NANDs. Okay, we will see this. This is just an overview. It's just a content slide. We will see this in detail. Okay. Now let's see logic functions of n variables. We have already seen this. 2 raised to n is our formula, right? Okay. Yes, so this is our NAND gate. So this is a NAND gate. It's a combination of, it's NAND. It's in its name. So it is nothing but not, this is our and if I attach a NOT gate to this, it will give me my NAND gate. So it is also called as knotted and. Knotted and. What is the difference? It is just having a bubble over here. So this bubble represents NOT function. Right? So obviously it will also invert the truth table. So in the first case, what was the output for a and output truth table was 0 0 0 1, but since we have inverted it, now our output will be 1 1 1 0. Right? It is just inversion. Okay. Now let's understand the properties of an AND. So these three properties show that NAND gate with both the inputs driven by the same signal is equivalent to a NOT gate. Right? Okay. NAND gate whose output is complemented is equivalent to a AND gate, and a NAND gate with complemented input acts as a OR gate. Right? Therefore, we can use a NAND gate for the elementary operators or the basic logic functions and, or, and not. In the next slide, I will show you how they have constructed the basic operations using NAND. Right? Okay. Let's see. Yeah, so you can see over here using the NAND gate, we have constructed the NOT. Using the AND gate, we have constructed an and using the NAND gate, we have constructed OR. Take a screenshot of this or just draw these circuits in your notebooks for the future reference, because while simplifying these circuits we might require this. Okay. Okay, now let's move on to the second type, that is NOR. So what would NOR be? It is nothing but OR gate added with NOT would give you NOR. Very similar, just invert the OR output. So the OR output was something like this, 0 1 1 1. Just invert this, it will give you the truth table of NOR gate. Right? Okay. Okay. And look at this slide, take a screenshot or pause the video and draw this in your textbook. Using the NOR gate, we have constructed the basic gates, not using NOR or using NOR and using NOR. Right? Very simple and easy. We are just revising it. Okay. Now next is XOR. XOR is also called as exclusive OR. Thing to remember is the symbol changes. It is simple OR symbol, but just added this thing, near the input side. Right? Okay. And in case of C, dot is nothing but considered as AND operator. Right? Plus symbol is considered as OR operator. Right? In case of XOR, plus with a circle, this is the symbol for XOR operation. Right? So now what is the XOR operation? When both the inputs are same, the output will be 0. See, look at the first condition and look at the last condition. A and B both are equal, 0 0 1 1. So the output is 0. Right? And when it is not true, the output will be 1. So this is the XOR operation. Very simple. Now what would XNOR be? Okay. Dot is nothing but AND, plus is nothing but OR, plus with a circle is nothing but XOR, and a dot with a circle is XNOR. This is our next function, XNOR. You can see what's the difference between an XOR and XNOR. You just add a bubble here. You can see there's a bubble here at the output side. Right? And what would happen? Just invert the XOR truth table. So our XOR truth table was, when the inputs are same, the output is 0 1 1. Just invert this, you would get the truth table for XNOR. Right? Now let's see the NOR equivalent circuit. Now see, this is the NOR symbol. Okay, now I've already told you this. How did we derive the NOR symbol? Or just add a NOT with it, and there is a bubble over here that you add that denotes the NOT function. That is nothing but inversion. Right? Okay. Okay, I think the slide has been copy pasted. We have already seen this, the De Morgan's theorem. Okay, now there is this. Okay, yes, you can see this universality of NAND and NOR. So NOR and NAND are called as universal gates, right? And or and not. These three are called as basic gates. These three are called as basic gates, and NAND and NOR are called as universal gates. You need to understand these two terms. What are universal gates? Mind my handwriting today. Okay. Right? So what are universal gates? NAND and NOR. What are the basic gates? OR, NOT, AND. Right? Okay. Now why do we call them the universal gates? Because using them we can form the basic gates. See, equivalent representation of AND, OR and NOT using NOR. Okay, take a screenshot of this. Here we have used only NAND gates, and we have the three basic gates, NOT and NOR, doing the same basic operation. Take a screenshot of this. I'll just erase the ink on the slide. Yes, this is a very important thing. You need to remember this, right? And this one is also very important. Okay, 1 second. If you want, I will just stretch this picture. I guess it's not visible enough. Okay, okay, I will put it later again on the Telegram group. The PDF will be available in the on the Telegram group, and the link of the Telegram group is in the description box. So you can join the Telegram group. You will have the access of this PDF there. Okay, yes. Now let's see representation of two NAND gate symbols. Okay, okay. So in here, when there is no bubble, it is called as active high, right? And when there is a bubble, it is called as an active low state, right? Okay. Similarly, you can see over here, now there is a bubble given at the input side, that's why this becomes an active low state. And here there is no bubble, so this becomes an active high state. So you need to understand the functioning of this bubble, very important. The bubble represents an active low state, right? Okay. Now what is the summary? We have seen the logic functions NAND and NOR, which are also called as the universal gates, because the basic gates can be formed from them, right? So this was just basics of the gates that we have studied till now, right? Just give me a second. You can take screenshots of this till then. Okay. Yes. So next is our Boolean functions, where we are going to learn to convert the equivalent of different circuits, and we are going to study the how to reduce the functions in the circuits using Boolean algebra. Okay. So thank you so much for today's lecture. I will end it here today, and I will meet you all, and I'll see you all in the next session, next live session probably. Till then, revise whatever we have studied in today's live session, and I've also given you the homework problems. Make sure you comment it down so that I do understand that you have actually understood. And if you have any doubts, put it in the comment section. The link to the Telegram channel is also in the description box. Make sure you join the Telegram channel, and I will be posting a new video, because I know all of you all are preparing for the UPSC 2023, sorry, 2024, and it is supposed to be on I guess it's 12th of February or 18th of February. I will just confirm it. And there is a video that we have prepared regarding the 2024 6-month strategy, right? Because today it's almost September, right? So you have like almost 5 months, I suppose. September, October, November, December, 4 months of 2023, and then 2024 you have 1 month of January, and February you have your exam. Right, February you're having your exam, so you need to complete your syllabus in these 4 months syllabus, and then January you need to solve your mock tests, right? And the notification will also be out in like 1 week or so. And I've also prepared a 6 month strategy for our engineering services examination 2024. That video also will be soon out. Okay, so I've prepared it. I will soon post it on our channel. So yes, we will end the session over here today. If you have any doubts, put it in the comment box, or you can message us on Telegram as well. So thank you so much everyone for watching. I will see you in the next video where we will study about the details of Boolean algebra, and we will solve some MCQs as well. Thank you so much for watching.